2025, question 13. It's an exponential modeling question. And I want to talk particularly about the challenge that a lot of students face when they're dealing with the early part of this question. And unlike a lot of other questions that are lots of marks, this particular question does basically require you to work out the unknown values a and k from part A in order to access the rest of the question. So it can be quite hard to pick up any marks in the later part of the question unless you've got at least something to work from for the first bit. There are a few follow-through marks, but the main bit you need is to be confident creating and verifying your exponential model. So first things first, it is a modeling question, and that means the very first thing we look for is what is being measured. There will be variables, so we look for the variables. The first thing I do as I skim through and realize it's a modeling question is pay attention to which letters represent the variables of the question. There are lots of letters in here. There's an H, an A, a K, a T, an E. E is just a number. It's 2.7 something. That's the exponential, natural exponential base. So that's not a variable. K and A are already described as positive constants. Those are going to be the values you're going to have to find for part A. That leaves H and T. And it describes those before it even gives you the equation. The height, H meters of this tree, T years after it was planted. So I'm going to write that down and make sure I know exactly what they represent. Because although it might be obvious at the beginning, as soon as you get down to part DII and they start talking about centimeters, your brain is not going to remember that height is measured in meters unless you deliberately write it down and look back at it later to double check. So I've written it here and we're going to come back to it. When we next read the information given, you'll see, and they often do this, it's in two handy bullet points. Each bullet point corresponds to a specific bit of information, and I can use that information to create my equations. All I have to do is recognize that if it says 10 years after it was planted, I can compare that to T years after it was planted. The phraseology will be almost identical, and we know that when T is 10, H is 6. And similarly for the next one, when T is 20, H is 11. Before I do anything else, I interpret that information in terms of T and H, and I write down two equations that correspond to it. So I've got the 6 equals 31 minus something, and then 11 equals 31 minus something. And then you've got to take stock. Figure out what you're dealing with. What do we need? We need the values of A and K. What do we have to work with? We have these two equations. Well, before I try doing anything too fancy, I'm going to simplify. I've got numbers on both sides of the equation. That's not necessary. Let's move it so that we only have a number on one side of the equation. And to make my life a little bit simpler, if I see some negative signs I don't like the look of, I might try to get rid of those as well. I've left these in this form. A e to the minus 10k equals 25, and a e to the minus 20k equals 20. So far, so good. Now, we're dealing with two simultaneous equations with two unknowns. So they should be solvable, but they're not linear. We've got a multiplied by something for a start, and then the something involves k in the power. So there's exponentials involved as well as multiplication. And it's not as straightforward as 3x add 2y equals 7 and 4y minus x equals 9. We're not dealing with linear simultaneous equations anymore. If we were, hey, we could let the calculator solve them for a start. But since we're not, we might need to think more carefully about the approach that we take. There are two main ways of solving simultaneous equations. One of them is substitution and one of them is elimination. Try to avoid thinking of simultaneous equations as set them equal to each other. That's a phrase I hear a lot, and it's not a helpful phrase because people start setting random bits of one equation equal to random bits of another equation. Or because both of them happen to have equals 7, you decide that you'll just set the left-hand side of one equal to the right-hand side of the other one, and you just end up with another equation that still has two unknowns. It's only helpful to set everything equal to anything else if you're actually eliminating one of the variables. So let's think about what that looks like in this context. We can either eliminate a variable through the classic adding or subtracting equations. If you've got 7x in one equation and minus 7x in the other equation, adding the two left-hand sides, for instance, might make all the x's disappear entirely. That's not going to work here. If you try adding the left-hand sides or subtracting the left-hand sides, you'll still have a involved, you'll still have k involved. So adding and subtracting, not going to work for us. We can rule that out as a possibility straight away. What about multiplying and dividing? Well, we're going to find that there is an approach that works here. You can do a multiplication or a division that's going to work out. So let's have a look at that to start with and see what it looks like. But then we'll come back to what I would suggest is probably a safer, more general option. Elimination is a little bit fancy, and if you can find an elimination that works, you might save yourself a little bit of time. But substitution for pretty much anything apart from the simplest simultaneous equations is almost always the best go-to approach. Even with that, as you can see, there's a couple of different options, but we'll come to those in a second. Let's focus on this first one, which is the elimination option. If we've got both equations written like this, a times something equals something, then dividing the left-hand sides of the equations will eliminate the value of a. We've got a as a factor of the left-hand side of each equation. So when you divide them, they cancel out. That's what's happening here. So a times e to the something divided by a times e to the something, you can divide the top and the bottom of this fraction by a. And as soon as a disappears, you've got an equation that only involves k. Now, it will be e to the minus 10k divided by e to the minus 20k, which might be a little confusing, but we've got index laws for this sort of thing. If you've got two exponential expressions with the same base and one's divided by the other, you can subtract the powers. Minus 10k take away minus 20k is positive 10k. And 25 over 20, you can leave it as a fraction, call it 5 over 4 if you like, or you can write it as 1.25. Once you've got to here, it should be plain sailing, as long as you remember that to reverse exponentiation, you've got to use logarithms. So the natural exponential base, e, goes with the natural logarithm, ln. So this is just log base e. And if you want to undo e to the power of, you do the natural log. Natural log of e to the power of 10k is just 10k. And the natural log of 1.25 is some messy number that you can ask the calculator for. When you've done that, you can divide by 10, and you've got a value for k. Now, in the question, it says find a complete equation for h in terms of t, giving the value of each of a and k to 3 significant figures. So when I get to this point where I've got some messy number for k, I can then turn it into a decimal and round it to 3 significant figures. From now on, it's safe to use that rounded version in later parts of the question. Depending on what they've told you, it's often a good idea to keep a more exact value saved on the calculator or keep it written in an exact form like a tenth ln 1.25. But if they've told you earlier in the question to give the values to a certain level of precision, you're safe to use those rounded values for the later parts of the question. Now, I'm not quite done. The question said find a complete equation giving the values of a and k. I've found k, I haven't found a, and I haven't written out the complete equation for the model yet. So I need to go back and find a. Now, one of the limitations with elimination method is that at no point do you have to rearrange the equation to get a in terms of k or k in terms of a until after you've already worked out one of the values. But it's not too bad, right? We've got an equation here, a times e to the minus 10k equals 25. If I now know the value of k, I can drop it in. E to the power of minus 10 times whatever k is, which I think is a tenth of ln 1.25. If that's already saved on your calculator screen, just use that. Keep it as exact as you can until you get to the very end, is my advice. So I've not put in 0.0223. I'm using the value from my calculator. So this might just be the answer button. We do e to the power of minus 10 times the answer, and then we divide 25 by that number, and that will give me a. Now I've got a number, 31.3. Last but not least, you write out the complete equation. There are 4 marks for this question. So if you've done 98% of the work and then you only get 75% of the marks, you're being underpaid. And that very often happens because when people finish doing all of the hard work for a question, they tend to move on straight away instead of going back and rereading the question. It says find a complete equation, so make sure you finish by writing the complete equation. We'll talk in a second about how we can check that these numbers make sense, but first, let's look at the substitution methods, because substitution generally is what I would advise most people to do for a question like this. The first thing you do is you figure out what you're going to substitute for. We have 2 choices. There are 2 variables. We've got 2 options. We can either make a the subject or we can make k the subject. So take a second and figure out which you prefer. If I said make a the subject of this equation, a times something equals something, or make k the subject of this equation, where k has been multiplied by 10, sign changed, e to the power of, then multiplied by a equals a number. Which one looks like it's going to take more work? Yeah, probably the k one. So instead of making k the subject, which is doable, but not ideal, I would suggest we make A the subject. Making A the subject only takes a single step. We divide by the number that A has been multiplied by. So A is 25 divided by e to the minus 10k. And of course, dividing by e to the minus 10k is the same as multiplying by e to the 10k. That's a negative power. And this is just a slightly nicer way of writing it. If you've got it written in a messier way, it'll still work. It just might slow you down, or you might have a greater chance of getting tripped up along the way. That's the only difference. And of course, you can do it with this one instead. A is equal to 20 times e to the 20k. But I've chosen to do it from the first equation, so I'm going to be using that throughout. So I like substitution. I think possibly it's slightly slower than the efficient elimination method, but it's going to be a better standard go-to approach because it will work in lots and lots of different situations. It is, for instance, the only way to deal with a straight line being solved simultaneously with a circle equation, because you're going to need to substitute from the line equation into the circle equation. So what happens next? We substitute. We've got our value for A in terms of k. We drop it in instead of A. So I've got 25e to the 10k. That goes in place of A in my equation. And I'm substituting into the other equation. So I've found A from equation 1. I'm substituting it into equation 2. And then you simplify using your your index laws. E to the something times e to the something else. Add the somethings. The powers get added when you multiply. And then we do a bit of rearranging. So we divide by 25. We've got e to the power of something equals 0.8. And then, just like we were saying before, you can get rid of the e to the power of by using the inverse function. The natural log does the opposite of e to the power of. So when you apply it to e to the power of minus 10k, you get minus 10k. And when you apply it to 0.8, you get the natural log of 0.8. And then we divide by the minus 10, and we've got a value for k. Now, some of you might be noticing that the value we got for k on this side and the value we got for k on this side look different. But I assure you, if you put it in your calculator, you'll find they give the same value, at least to have many messy decimal places the calculator gives. The reason for this is log laws. There's a negative sign outside this one, and there isn't outside this one. The 1/10 is the same, so the only issue is the log of 5 over 4 the same as the negative log of 4 over 5? And maybe writing it in fractional form will help you to see why that's true. One of the log laws allows you to turn a power inside a log into a scaling factor outside the log. So a -1 outside the log can be pulled inside and turn the inside into its reciprocal. This is why sometimes a student will think they've got an answer wrong because they got the natural log of 1/2 and I got the negative natural log of 2. They're the same answer. They just look quite different. And it's a little tricky for our brains to get our heads around that. This is a positive value because the natural log of something smaller than 1 is a negative number. Okay, so we have our k value, and you can see it took a similar amount of time to the elimination method over here. Relatively nice and efficient. And now we've got k. We can do exactly the same thing we did for the other one. Sub it back in to find a. So we've got this number on our calculator. A slight advantage that we already have an equation rearranged. So we've got a in terms of k. We just drop the value for k in, and out pops the value for a. Just for completeness, we'll have a quick look at what happens if you decide you're going to make k the subject. It's not wrong, it's just a bit of a long way round. We would have a few steps to make k the subject. We'd have to divide both sides of the equation by a, and then we'd have to take the natural log of both sides, and then we divide by minus 10. You'll recognize the steps because we ended up doing a similar thing later on in here, but it's a lot more work to then substitute that in and simplify the result. Look at this. We've got e to the power of something multiplied by a fraction multiplied by the log of another fraction. There's a lot going on in there, and you can tidy it up. Minus 20 times minus 1/10 is 2, and we can use the log laws to bring that 2 inside the logarithm to turn it from 2 log something to log of the something squared. And then e to the power of natural log of something is just the something. That's how the natural log works. It's the perfect inverse of e to the power of. And then we've just got to be careful with our fractions. Square the top, square the bottom. 25 over a multiplied by 25 over a is 625 over a squared. And we've got an a multiplied by it on the left-hand side there. So we get 625a over a squared, We can then divide top and bottom by a to get 625 over a. And finally, divide both sides by 20, multiply both sides by a, and we've got a fraction value for a. And we can round it to 3 significant figures as requested in the question. As you can see, a bit of a slog. Once you've got one of the values, sub it back in to your expression for k, and you can find the other value. So at least that final step is relatively quick for all 3 methods. Finally, for this part of the question, how do we know this is plausible? Well, the fact that 31.3 is similar to 31 is encouraging. And the things I'm looking for to do this will be the same things I'd look for if I was asked to sketch the graph of this model. I'd ask myself what happens at the beginning when t equals 0, and what happens in the long run as t gets bigger and bigger and bigger. And as it happens, both of those things are the subject of parts B and C of the question. So instead of spending time thinking about it right now, we're going to move ahead to look at B and C. But bear in mind, even if the question doesn't give you a mark or two for specifically calculating those things, you can always ask yourself, are these numbers sensible? By saying what happens at the beginning and what happens in the long run. We're talking about the y-intercept effectively and the long-term behavior. So let's take a look at part B. Part B is asking us to deduce the limit to which the tree can grow. In other words, there is a value of h that we'll never quite reach. And the best way to understand why is to think about what we know about exponential decay. When you have e to the power of minus x, or e to the power of minus t, or e to the power of minus 0.02t, or whatever it might be, it is an exponential decay. It means as t gets bigger and bigger, e to the power of negative something times t gets smaller and smaller and smaller. In fact, it's going to get closer and closer to 0. And if you just drew the graph of y equals e to the minus x, you would see that it's approaching 0. It has an asymptote at y equals 0 on the x-axis. Well, we don't just have that. We've also multiplied it by this number, and there's a minus sign in front. And then there's some other numbers in here. But the simplest way to think of it is, I know what this piece is doing. E to the minus 0.0223t is getting closer and closer to 0 as t gets bigger and bigger. And if you're not quite sure whether it's getting bigger or smaller, try plugging in a big value for t. If you put in t equals 100, pretty sure you'll get a really, really tiny answer. Put t equals 1,000, it'll probably be so tiny the calculator will just tell you the answer is already 0. So no matter how big t is, this thing is only ever going to shrink smaller and smaller and smaller. And if you multiply a tiny, tiny number by 31.3, well, you still just get a tiny, tiny number, just not quite as tiny. It's still approaching 0. And so h is approaching 31, take away 31.3 times 0, which is just 31. So we have a hard limit of 31 meters, and that's where your asymptote would be. This is an exponential decay, but because of the minus sign in here, it's actually decaying upwards from something small up to, but never quite reaching 31. A bit like if you drop something out of a plane, it's going to speed up until it gets close to its terminal velocity. But as it gets closer to its terminal velocity, it speeds up less and less. So it gets closer and closer and closer, but technically never quite reaches terminal velocity, at least according to the pure mathematical model. In reality, your terminal velocity will change as you move around, etc., etc. So it gets a bit messier. Part C is asking about the initial value. Find the initial height of the tree. The word initial is one of those words that will come up a lot in modeling questions, just like the word rate. If they talk about rate like they do in DII, we know we're dealing with derivatives. The rate at which something changes is the gradient of that function. And when they talk about initial, they're referring to what happens at the beginning. So t equals 0. So we just substitute t equals 0. And if you do that, you find a value for h, which is small, but it's not 0. You would expect that when a tree is planted, it has a height of 0. But this model seems to suggest it has a height of minus 0.3 meters. Now, that doesn't mean you're wrong. It just means the model is not perfect for all values of t. We got the values of a and k by using these two facts, the 10-year height and the 20-year height. And then we kind of extrapolate outwards, and the model is probably not going to be perfect for things like 2 years old or 30 years old. It's going to be good at 10 years and 20 years, and it's going to be good in between 10 and 20 probably, because you'll be interpolating. But if you go too far beyond the scope of the model, you might get weird results. And that's what II is about. This is the bit where you're evaluating the model, and we're saying you can't have a tree with a negative height. Therefore, the model is not suitable for the early growth of the tree. That's all they're looking for. And finally, part D. We have a rule for differentiating. If they ask you for dh by dt, the derivative of h with respect to t, first small point, this is h in terms of t. It's not y in terms of x. So avoid writing dy by dx. I know most of the time when you're working with derivatives and you're doing calculus, we have y as the output and x as the input. But as soon as we start dealing with models like this, the variables could have all sorts of names. So get in the habit of using the names of the actual variables in question. Next, to differentiate, a constant is just 0. So 31 differentiates to 0. To differentiate any multiple of a function, we just have that multiple of the derivative of the function. And that leaves us with just the exponential term. E to the t differentiates to e to the t, and e to the something t differentiates to something times e to the something t. So whatever the number is in front of t, that comes down in front, but the power doesn't change. This is because the exponential function is essentially designed to be the function that differentiates to itself. But if you scale it by making it, instead of e to the x, you make it e to the kx, then you're stretching the function. And the effect of the stretch is to stretch the derivative. So you end up with a steeper function than you otherwise would, or a shallower function, depending on whether the value of k is large or small, positive or negative. And it can even flip it over, like in this case. So the slope of this is going to be minus 0.0223 multiplied by e to the minus 0.0223t. And they do say give your answer in its simplest form. So they'd be looking for you to actually multiply the minus 31.3 and the minus 0.0223 together. And this is what we should get. Now, there might be some small discrepancies with the actual numbers you get after you do your rounding. And that's normally because you've either used a more exact value or you rounded too soon somewhere else in a question. If they've asked you to give your answers to the original question to 3 significant figures, keep using those rounded values throughout the rest of the question to be on the safe side. And in that case, you should get something that rounds nicely to 0.698. The final part of this question, they tell you in the question, hence find the value of t for which the height of the tree is increasing at a rate of 30 centimeters per year. This is where coming back to what we wrote about the variables in the question is really useful. H is measured in meters, t is measured in years. There's no variable there that's measured in centimeters per year. Centimeters per year is a compound measure that combines height and time, but it's not meters per year, it's centimeters per year. So we've got a small modification to make first. If it's changing at a rate of 30 centimeters per year, then the height in meters is changing at 0.3 meters per year. So dh by dt, which is the rate at which h changes over time, is 0.3. And that's the equation we're solving. So you just set 0.3 equal to this. We divide by 0.698. We take the natural log of both sides. We divide by the minus 0.0223. And then finally, you round your value to a sensible level of precision. If they haven't specified the level of precision that they're looking for, then they'll often have something like anything which rounds to. In this particular case, the official mark scheme actually says 37.9, but in the notes it says anything which rounds to 37.7, 37.8, or 37.9. But note that this may be scored if k is rounded in A. In other words, they're being a little bit flexible at the end, depending on how much you've rounded things earlier on. So you don't need to worry too much if you've been consistent and sensible and you've not rounded too much too soon, then your values will be fine.